Pro Vice Chancellor, Research and Development Affairs, and Dean School of Basic and Applied Sciences, our honorable invited speaker, Professor Parthasarathi Majumdar, convener, Professor Aparajita Bhattacharya, our head of the department, Dr. Moumita Dey, all my fellow colleagues, and all the participants of the virtual webinar. Good afternoon, everybody. We have assembled here today on the occasion to celebrate the birth anniversary of legendary physicist and teacher Professor Satyendra Bose. In the beginning, I, Dr. Purva Bhattacharya, will like to take this opportunity to offer my deep homage and respect to Professor Satyendra Bose through the following few words. Professor Bose was born in Kolkata on 1st January in the year 1894. He attended Hindu school and later on attended Presidency College in Calcutta, earning the highest marks at each institution. Another great leading light in physics of our country, Professor Meghnad Saha, was his classmate. Both of them came in contact with teachers such as Sir Jagadish Chandra Bose and Acharya Prafulla Chandra Rai, who provided inspiration to aim high in life. As is well known to all of us, Professor Satyendra Bose was one of the greatest Indian mathematicians and physicists specializing in theoretical physics. He is best known for his work on quantum mechanics in the early 1920s, collaborating with Albert Einstein in developing the foundation for Bose-Einstein statistics and the theory of Bose-Einstein condensation. The class of particles that obey Bose-Einstein statistics, bosons, was named after Bose by Paul Dirac. Besides physics, he had a wide range of interest in different fields, including mathematics, chemistry, biology, mineralogy, philosophy, arts, literature, and music. He served on many research and development committees in India. Not only that, he was well versed in several languages such as Bengali, English, French, German, and Sanskrit, as well as the poetry of Lord Tennyson, Rabindranath Tagore, and Kalidas. He could play the esraj, an Indian musical instrument. He devoted significant time to promoting Bengali as a teaching language, translating scientific papers into it, and promoting the development of science in the region. To achieve this goal, Bangio Bigyan Porishad, a pioneer science organization for cultivation and popularization of science and scientific knowledge, was founded in the year 1948 by the collective efforts of all the eminent scientists and educationists of Bengal under his leadership. Professor Bose was honored with title Padma Vibhushan by the Indian government in 1954. In 1959, he was appointed as a national professor, the highest honor in the country for a scholar, a position he held for 15 years. Bose became an advisor to then newly formed Council of Scientific and Industrial Research, CSIR. He was the president of the Indian Physical Society and the National Institute of Science. He was elected general president of the Indian Science Congress and was the vice president and then the president of Indian Statistical Institute. In 1958, he became a fellow of the Royal Society. He was also nominated as a member of Rajya Sabha. Professor Bose was nominated several times for the Nobel Prize in Physics for his outstanding contribution to physics by developing Bose-Einstein statistics and the unified field theory. In recent years, this statistics is found to be of profound importance in the classifications of fundamental particles and has contributed immensely to the development of nuclear physics. It is unfortunate that finally he was not bestowed with this honor. When Bose himself was once asked that questions, he simply replied, "I have got all the recognition I deserve," probably because in the realms of science to which he belonged, what is important is not a Nobel, but whether one's name will live on in scientific discussion in the decades to come. He left for his heavenly abode on 4th February 1974. With this note, I want to end my address with deep thanks to all the concerned, the authorities of the university, the head of the Department of Physics, and different staff member, my fellow colleagues in the physics department for their guidance, support, and efforts to make this program a success. So may I now request Professor Jitendra Kumar Pandey for a few words on this occasion. Professor Pandey, who did his PhD from National Chemical Laboratory, Pune, having almost 20 plus years of research and teaching experience in national and international institutions. His research areas are in bio, nanocomposite, degradation and stabilization of polymer composite, nanomaterial for water treatment, synthesis, characterization, and analysis of reinforced composite. He has published more than 100 research articles, 17 patents, 5 books, and successfully completed various research projects from the Department of Science and Technology, Government of India. Dr. Pandey is a member of the National Academy of Sciences, India. He is also the recipient of Brain Pool Fellowship from Government of South Korea, Max Planck Fellowship from Germany, and Fellowship from Japan Society of Promotion of Sciences, Japan. So I will request Professor Pandey, can you please speak few words for us on this occasion, sir?
Thank you, Purva, Papia, and everyone here. You know, when you read about Professor S.N. Bose, somewhere in some corner of your heart, you feel sad. He was such a hard-working person, the only son with 6 sisters, born in a very small village of Nadia. From there, he came in contact with great teachers like T.C. Ray, J.C. Bose, and wherever he studied, he was always first. He stood always first. And each and every person who know even little bit about physics, he can tell you that Bose was the most deserving person for any prize, for any top prize. It's not only Nobel for in the field of physics. So that two things, is definitely that feels like in science also sometimes mistakes happens. Even you might be the top body, apex body of prize or apex body of science, but sometimes mistakes happen. His life was full of struggle. His life is an inspiration. The way he started his career from a small village and he ended to the presidency college. And I think many of us might not even remember the name of that village. If Bose was born in Japan, Korea, or some other such type of nations, you would have seen, biggest, uh, the biggest tourist, at least science tourist spot for anyone who was coming to India. I am sure that with the time these things will change. And thank you, Physics Department, for starting this series. And it is first, it's historical, and I am grateful of Partha sir. He's here. He agreed. Grateful of Dr. Bhattacharya to get in touch with him. This is the beginning, and I'm sure we will reach up to 50th SN Bose lecture, then 100th SN Bose lecture. We may or may not be here, but you guys in physics department, you have started something that will remain with us. So thank you everyone, and thank you Partha sir, and we are just looking forward for your lecture. Thank you.
Thank you.
Thank you, sir. So may I now request Dr. Papia Dhara to please introduce our honorable speaker to our participants. So Dr. Papia Dhara, Assistant Professor, Department of Physics, has done her PhD from IIT ISM Dhanbad. She has received prestigious international doctoral fellowship from European Commission and has worked with established group of Politecnico da Torino, Italy. She is recipient of international postdoctoral fellowship from University of London, UK, and her current research area is photonics optical fiber sensor. So I will request Dr. Papia Dhara to please take over from here.
First of all, thank you so much for this nice introduction. I'm really impressed. Thank you so much. So Good afternoon to our distinguished speaker. First of all, Professor Parthasarathi Majumdar sir, all the participants who are mostly faculty members here, students, and obviously our respected Dean of School of Basic and Applied Science, Adamas University, Dr. Jitendra Kumar Pandey sir, and HOD of Physics, Dr. Momita Madam, convener of today's lecture, Professor Aparajita Bhattacharya Madam, and who have gathered here today for first Satyendra Nath Bose Memorial Lecture 2022. So I would like to welcome you all and thank you for taking the time off to join us in this deliberation. So always it is our great opportunity for me to introduce such a respected speaker. Professor Parthasarathi Majumdar sir, who was former senior professor at multiple premier institutions in India, such as Institute of Mathematical Sciences, Chennai, Shah Institute of Nuclear Physics, Kolkata, RKM, Vivekananda Education and Research Institute, Velumot. Currently, he is visiting professor at Indian Associations for the Cultivation of Science, Kolkata. Professor Majumdar is alumni of Brandeis University, USA. He was associated with University of Maryland, USA, TIF for Mumbai after that. In 2018, he was elected as Fellow of the National Academy of Science, India, which is started by Nath Shah, Professor Nath Shah. He has remarkable contributions of solar energy devices. His current research interest is on gravitational theory, physics of black holes, high energy theory, gauge field interactions, standalone low voltage solar devices. He has more than 100 publications in reputed international journals. So this is what I can mention in very few among his outstanding contribution towards science. So now, without further delay, I would like to request Professor Majumdar sir to deliver his talk on the magic of bosons, photons to gravitational waves. Sir, please deliver your talk.
Thank you very much, Papia. That was a wonderful introduction, probably much better than I deserve. My achievements are actually quite modest because we are speaking about a superstar, Professor Satyendra Nath Bose, and to talk about one's own achievement in that context is a joke. However, I should say that today, on this occasion, I have decided not to simply eulogize Professor Satyendra Bose because we've heard a lot about that. Eulogies are very common in India, and I think it's a little unfortunate because I think for a scientist especially, it's important to be very critical. Okay, so I am probably going to be a shade critical of certain aspects of Professor Bose because I think we haven't seen an intellect of his caliber in India, in post-independence India, or even pre-independence India for a long time. I mean, I have had the opportunity of seeing him a few days before his unfortunate demise, when there was a meeting in Kolkata University, Calcutta University, honoring his contribution. That was the first and last time I saw him, and I was very sad to learn that he passed away soon after. However, today, what I would like to do is to focus on the science that we all celebrate. Focus on the science in the sense that focus the historical context and focus on the outcomes of this great contribution. So I shall share my screen. And I think I'm co-host now. So yes, I can share my screen right away. Right. So Purva or Papia, would you please let me know?
Yes, sir.
Yes, sir.
Yes,
Yes.
Yes, sir, we can.
You have my phone number, so if it happens that...
Yes, sir, it's completely visible. Yeah,
okay.
it's changing.
So let us begin at the beginning. We're going to talk about bosons. Of course, they are named after Bose, Satyendra Bose. They're called bosons, and I shall go to the history also of where the name came from. And we're going to cover a reasonably large area, begin with photons to gravitational waves. We shall give an overview. So this talk is going to be semi-technical. It's not a physics seminar in the sense that it's not a technical talk at all. However, it's also technical in the sense that we shall not be talking about his life or what he had lunch with and that sort of thing. So it will just be on the physics that he did. So in that sense, it is technical. However, I shall not write down many equations, and because I realize that a large part of the audience is probably young students who are just beginning their physics education. So for them, it's more an inspiration. Where did it all begin? Well, of course, I think most of us are familiar with the fact that light consists of electromagnetic waves. And this is the great theory of James Clerk Maxwell in the mid-19th century. So waves are supposed to be changing electromagnetic fields. Electromagnetic waves are changing electromagnetic fields. And you can see from this picture, and I think this cursor is visible, is it not? I think this cursor, well, this little pointer is visible.
It's visible, sir. This is visible.
It is visible, very good. So here in blue, you see oscillations of the electric field as a function of distance. And you can see that the distance between the two crests is, of course, the wavelength. And the red thing here, the red field here is the magnetic field. And you can see that there are oscillations. So at any point, the oscillations of the electric field and magnetic field are actually perpendicular to the direction of propagation. That is what we mean by transverse electromagnetic waves. They are transverse. They're always perpendicular to the direction of propagation. Couple of things about fields. First of all, they're not just changing with space, not just with the length, but also with time. So if you fix yourself at any one point, you will see at that point that the electric field and magnetic field are going up and down, okay, as a function of time. So they are like harmonic oscillations, okay? And the whole thing is then moving periodically. So the wave is a periodic field in both space and time. It has a frequency and it has a wavelength, okay? This is known to most of you. The question is, how are they generated? Now, Maxwell showed us that they are generated by the motion, accelerated motion of continuous charge distributions. Now, here, this is important to specify what I mean by a continuous charge distribution. So there's a picture here from the internet. This picture shows a continuous charge distribution, a bag of charges, as it were. And the thing about this bag is that there is not a single point in this bag which does not have a charge. So the charge is continuously distributed throughout this pink bag, okay? Right, and so if this kind of a bag then moves through space with an acceleration, that's what would generate this kind of a wave, okay? And this is the simplest picture. And of course, I will write down a few equations, very, very few, don't get worried. This is Maxwell's wave equation. Here, the A, which is a function of space and time, is the vector potential, okay? And I'm sure many of you have heard the vector potential. Those of you who haven't, just learn that the vector potential is such a quantity, first invented by Michael Faraday and then converted to mathematics by Maxwell, whose derivatives with respect to space and time give you the magnetic field and the electric field. So writing down the vector potential is very convenient because it captures both the electric field and the magnetic field. However, you must remember that this field also is a very continuous quantity. Look at the light in your rooms. Every point in your room, and there's sunlight now, has light coming in, right? There's light in your rooms everywhere, but there's of course more light somewhere, more intense light, and some other points have less intense light. Okay, I'm sure that's the case in everybody's room, whether you have lighting from artificial sources like lights, like lamps, or you have natural lighting like the sun. Okay, so that's the point. So then the question is, what is this equation? So here we have the continuous charge distribution moving. That constitutes a current. It's a current density, really. So that's a current per unit area per unit time. That's basically moving charges. So the source of this wave, so the box squared, I should tell you a little bit about the box squared, because this is a great invention of a French mathematician called D'Alembert, who basically said that if you take an object and apply this operator on that object, then this operator will pick out for you the part which is relevant to a wave. Okay? And that operator also has what is the velocity of that wave. So this is a very convenient operator. And therefore, this is called the wave equation, Maxwell wave equation. Remember that both sides are continuous. They're continuous meaning that there is no part in space and time which does not have A. And likewise, there's no part in space and time which does not have J, the continuous source distribution, the current. However, in 1905, Einstein realized from the experiments that were ongoing at the time that charge is quantized. Charge is not continuous. Charge in the universe is always the multiple of some fundamental unit, which is usually the electronic charge, right? So the electronic charge serves as the unit, but every charge in the universe is a multiple, which means that you can count it. It could be a lakh or a crore times that unit, but still a number. It's not a continuous distribution which cannot be counted. So if you have a continuous distribution like light in this room, you cannot count it, you see. It's very difficult to count it. Like, for instance, the matter on whatever, your computer or table or whatever. What is the matter? What is the matter made of? Well, now you know that it's made up of charges, right? Electrons. And each electron is very, very tiny. It's a tiny bit of matter, but it can be counted. The number of electrons can be counted. It's not a continuous infinity. So this is what I call a discrete distribution. So instead of that little pink thing in here, what you have is a discrete distribution of charges. And it is the motion of these charges which will now constitute a current. But then Einstein said, there is a problem here. You have an equation which is continuous on the left because it produces non-countable electromagnetic fields. On the other hand, the right is supposed to be countable. How can that be? How can countable bits of charge, which is countable bits of matter really, generate non-countable electromagnetic fields? So there, mathematically, that is not the question. You can use some mathematical apparatus to describe that, but physically, there seems to be a little problem, right? You can count the right-hand side because you have a number of charges here and the number is known, maybe could very, very large number, but still a known number. Here, this you can't count. So that is why Einstein raised this question in 1905. And then he went further to point out that if you indeed persisted with the Maxwell theory, you'll have a problem. What is the problem? Well, I'm going to talk about this, that there will be a contradiction between emission of light from matter, during the emission of light from matter, which is black body radiation, I'll come to that in a minute, and during the transformation of light into matter. So this is a direct quote from Einstein's 1905 article. He was talking about two physical phenomena which contradicted Maxwell's idea, Maxwell's equation, if you believe that charge is quantized. Charge quantization, therefore, leads to contradictions. So if you have only radiation, okay, if you have only radiation, there's no matter hanging around anymore, or if you have converted the energy of light into matter, like in the photoelectric effect, then you have a problem. Now, today I shall not talk about the photoelectric effect unless there's a question at the end, but I shall focus on the black body radiation. So what's a black body? Well, any object which absorbs incident radiation is basically a black body, but here a black body is the most efficient radiator. It absorbs all the radiation that is incident on it. And then, of course, when the temperature outside goes down, this black body radiator will emit. So it gets to some equilibrium temperature after absorbing all the radiation, and then it starts radiating. So these little lines, wiggly lines here are supposed to be radiation coming out of the black body. And what one sees is that the strength or the intensity of this radiation is only a function of the temperature of this black body radiator's equilibrium temperature. Okay. And of course, the black body is a hollow, let's say, metallic object, metallic sphere with a hole through which the radiation comes out. There is no matter inside this black body, and that is why we're talking about matter in the sense that whatever radiation was there is bouncing from the walls of this black body. There's continuous reflection. Standing waves are set up, and then they come out. So you might say, well, okay, so these are electromagnetic waves. We can use Maxwell's theory to calculate the radiation as a function of temperature. We bring in thermodynamics through the classical thermodynamic laws, which were enunciated by Wilhelm Wien, called the Wien's displacement law, and also by Stefan Boltzmann law. This is something you learn about, and I shall briefly mention these laws in a minute. And of course, there was a humongous problem, which many of you would know, and this is called the ultraviolet catastrophe. So the classical theory based on the Maxwell equation is here. And for large wavelengths which are large meaning this is in micrometers. So let's say beyond 2 micrometers 2 micrometers, the theory is actually good. This works. But when you come to smaller and smaller wavelengths, that is to larger and larger frequency, and here also the temperature parameter is mentioned. So suppose you are looking at 5,000 degrees Kelvin, that's equilibrium temperature. In that case, the classical theory would give you this curve, right? And yet, if you do experiments, like many people did in the late 19th century, they were doing experiments with black bodies. Basically, they were designing electric bulbs and trying to see what color would produce what kind of radiation. And they ran into a problem because experimentally they found these curves, which I have drawn here. This is the visible spectrum, visible part of the electromagnetic spectrum. Higher wavelengths in this direction are infrared. Lower wavelengths or higher frequencies are ultraviolet. So that's the spectrum. And you can see that this curve does not rise up all the way. It just comes down. So indeed, there's a maximum of radiation as you come down in wavelength or increase in frequency. So indeed, this ultraviolet catastrophe, which tells you that, this curve goes infinitely large in the ultraviolet, is really not there in nature. Nature does not allow things to increase without bound. What is happening? Well, it seems that these people who made light bulbs approached Max Planck, who was a professor in Berlin University. And of course, Planck realized that Maxwell's theory had to be changed. But he also had to do something quick because these light people wanted a quick answer so that they could go back to their business. So what he proposed is that the walls of this black body radiator had oscillators. What oscillators? Well, nobody knew at the time, nor did Planck for that matter. And he just postulated that these oscillators emitted little packets of radiant energy. So it is not, this is something very weird because from your experience with harmonic oscillators that the energy of a harmonic oscillator is actually continuous. It does not come in packets. So what was Planck talking about? Well, this is called the Planck quantum hypothesis. He just said, out of the hat, that these oscillators must emit quanta of radiant energy, packets, little packets. And you also would know that the energy of an oscillator, of a classical harmonic oscillator, does not depend on the frequency. It depends on the amplitude. You remember what that is? Well, you can convert that into a dependence on the frequency as well, but the main dependence comes from the amplitude. However, here it is only a function of the frequency. So the formula which Planck wrote down is so simple. He said the energy of these oscillators, the minimum energy quanta would be just h bar Planck constant times the frequency omega. Okay. But of course, the mysterious thing was, where are these oscillators? Do we see these oscillators? You say that they are hidden in the wall. The wall we know is made up of some metal, copper or something. So what oscillators are we talking about? That was a big mystery. But what Planck succeeded in doing is to produce these curves, you see. That was a great success. So Planck's hypothesis, incomplete as it was, still succeeded in producing something which the light bulb makers appreciated very much. So they went back and saying, yeah, now we know how to design our light bulbs, which was very nice. Einstein, who came 5 years, well, he was there when Planck was proposing his hypothesis. He was very deeply influenced by it. But he came up with a totally different hypothesis. A different hypothesis which immediately removed the mystery associated with the Planck hypothesis. Einstein went to the extent of saying that light, which are electromagnetic fields from the Maxwell construction, consist of indivisible massless quanta, which are called photons. Nowadays we call photons, we just call them quanta, which propagate through space. These massless quanta do not join up or divide, they just propagate free stream, simply like that, okay? And their energies are given by the frequency, E equals h bar omega, and their momenta are given by h bar times k, where k is the wave vector. The magnitude of this vector k is 2 pi over the wavelength, okay? This is the formula which he proposed. This is the formulation which he proposed. He was talking about massless quanta. Now here, I'd like to make a point that, again, I forgot to look at when I started. So look, I mean, can I get a warning when it's half over, half an hour or something? I mean,
so it's not like warning, but I will intimate you.
Yeah, just let me know, right?
Yeah.
Because I have lost track of the time, which always happens.
Okay.
Now, so what I was saying is that this is a bit weird because you have heard about the corpuscular theory of Newton. However, there's a big difference, and the difference is the word massless. In Newtonian mechanics, in the entire Newtonian philosophy, any particle without mass does not have an existence. And this is where Einstein, through his discovery of special relativity, would go beyond Newton. So he was talking about particles without mass, which carry energy and momentum, like here. And the energy and momentum, you can see, are proportional to each other. E is simply P, the magnitude of the momentum times the velocity of light. Light is simply omega by k. Omega by k is the velocity of light, c. So that was the difference. So he's talking about massless quanta, okay? They are called the photons. The photons are different from the old corpuscular idea. And he was proposing a change in the entire way you think about electromagnetic fields. So electromagnetic fields are no longer continuous. They are also made up of discrete, countable photons. This was a dramatic change. And of course, the first thing that he would have liked to do, and everybody who learned about Einstein's hypothesis would have liked to do, was to use this hypothesis rather than Planck's oscillators to discover Planck law, to rederive Planck law. And there, everybody got stuck. This is 1907-08, all the way, well, we come to all the way, for about 19 years, till about 1923. Okay, that went on. So this is really fantastic that this happened. I mean, you know, they're all very, very smart, talented people struggling very hard to derive Planck law. So what was Einstein stuck with? He was stuck. The great Albert Einstein was stuck. He was stuck because he was unable to remove the assumptions of classical electrodynamics and the idea that we must have a correspondence. So he was, in fact, trying to tag photons as if they were like gas molecules. Now, when we do ideal gases, all of you have done some theory of ideal gases in your first year of college, we treat the molecules as distinguishable. And indeed they are, because you can think of molecules as rigid spheres which collide and produce all the thermodynamic quantities that we observe. And you know, here are the classical assumptions that we make. Classical thermodynamics gives you Wien's displacement law, which I mentioned, and also Stefan Boltzmann law. So Einstein was very much tied. So on the one hand, he was introducing a dramatic, radical proposal for the description of electromagnetism. On the other hand, in order to derive the Planck law, he was stuck. Okay? And he was trying to think of photons just like gas molecules. So a bunch of photons, a collection of photons, which is the light in your room, for him would look like exactly like the oxygen in your room. Are they the same? They're not. They're not. And that is where Satyendra Bose came in. What if the photons were actually indistinguishable? You couldn't tag photons. Now, here's a story which, you know, I've heard. I don't know whether this is a true story or not. You see, in the 1920s, Satyendra Bose had moved from Kolkata, where he was already professor in the University College of Science. He had moved because he had obtained a higher position at the University of Dhaka in the physics department, Bangladesh now. And in Dhaka, he was teaching a class. He was teaching what was then, you see, this is the most important point. He was teaching in his class, in his master's class, what was then top level physics, frontier level physics. And while teaching the course, the story goes that one of the students said, "Why are you distinguishing photons? Why should photons be like gas molecules?" And for a moment, I believe Satyendra Bose in his lecture was stumped. He was otherwise, as Papia and Purba mentioned, he was a brilliant lecturer. Professor Pandey also mentioned. He's a brilliant lecturer, but he was stumped. He didn't have an answer. And what he did then was to go and figure out, what if they were not distinguishable? And this is the key. This is the key, because at that point, he realized that if they were not distinguishable, they will do strange things. They will do outstandingly strange things which gas molecules couldn't. For instance, if you look at these two diagrams here, here I show photons, or well, right now they're just photons, but this is just the distribution of photons. So what are we trying to do? What is the law? The law gives you the energy distribution of, say, a fixed number of photons at a temperature T with some total energy which is fixed in an enclosure, like a black body, right? Right here. And so here, this is what the old way of counting, the Maxwell-Boltzmann way, which Einstein employed. Here you can see that you have molecules which could be the same gas, and yet they're rigid spheres. So if you put two molecules in the lowest energy state, then in the same energy bin, this molecule would behave differently. So you will be able to distinguish this molecule from these two. There's no molecule in this energy bin. These are energy bins, bins which carry a certain amount of energy. In the same distribution, the same number of particles were to be done in the Satyendra Bose way of doing it, you would treat all the three here as identical and all the two here as identical. And then, of course, instead of the energy bins as little boxes, you have just partitions. That's good enough. And the partitions look, one is absolutely alike the other. Here also is the same. So then you have two indistinguishable classes of particles. One is the photons, the other are the partitions. And then you seek the number of ways in which you can arrange these two objects, the partitions as well as the photons, with any number of particles being in any bin. So between any two partitions, there can be any number of particles. Of course, then we focus on the total number of particles being fixed and the total energy being fixed. These are constraints on the system. And we look for the configuration of these particles, which minimizes the energy at a given temperature. He did this calculation, and without any assumption, Planck law popped out right here. This is the Planck radiation law given by Planck, and he was able to reproduce it. So he was elated because he had solved the problem, which maybe some smart student in class had asked. He was absolutely elated and wrote a paper immediately, very quickly, and sent it to Philosophical Magazine. And after a few months, that paper came back saying that, no, this paper does not have enough content to be published in Philosophical Magazine. Philosophical Magazine at that time was an extremely well-known British physics journal. So it came back from there. Philosophy, the word philosophy has to do with the fact that physics used to be called natural philosophy at the time. Okay, so I'll come back to the three consequences in a minute, but I'd like to share with you a story which I've heard from Professor Partho Ghosh, and I'm simply constructed a kind of little drama. So there is a factor of 2 here, okay? And a lot of debate actually happened around this factor of 2, which you might think is inconsequential, but it's not. Because you need that factor of 2 in order to agree with the correct version of the Planck law, which Planck had been able to work out. So, in his original version of the paper, Satyendra Bose wrote it as it originating from the spin states of the photon. Spin within quotes, because in 1924, spin of a particle as an intrinsic property that we know now was not known. It was just being discovered. People had just seen the spin of the electron. Well, that's one thing, but what is the spin of a photon? So Einstein, after the rejection from Philosophical Magazine, S.N. Bose sent the paper to Einstein with a beautiful letter saying that you are our teacher, I have done this work, I've been able to reproduce Planck law without any classical thermodynamic or electrodynamic assumptions. Please have a look. And if you think it's fit, please publish it in Zeitschrift für Physik, which is the top journal in Germany at the time. Germany was, of course, at that time, the leader in physics. Here, the word spin, Einstein didn't like. He said, what spin? What do you mean by the spin of a photon? We don't know that yet. So what he did was he wrote, if you read the version of the paper that is available, it says the 2 originates from the 2 polarization states. And this is where S.N. Bose differed. He said, why should a photon, which is a quantum particle, have polarization? Polarization, as we know, is a property of classical electromagnetic waves. Why should that have polarization? So what is the present understanding? So we make a jump cut from 1925 to 2022. And now we know, of course, that actually, Satyendra Bose was right. Photons do have spin. But the photon, now if you just for a moment think that it was this vector potential, which tells you about light, the vector potential is a vector, and usually we associate a vector with spin 1. And you also perhaps know that if you have spin s, then the number of spin states is 2s plus 1. So photons should have 3 spin states. Not 2, but 3. So where does the 2 come from? Well, and that's the key. Photons are massless. So the 3 spin states works in a reference frame which can be brought to rest, a rest frame, because you need a z direction or any space direction. So if you want a space direction around which is invariant, okay, you will need a rest frame. But photons are massless. They're always moving at the velocity of light. So there is no rest frame. But they do have a direction associated with them, and that is the direction of the wave vector, the momentum of the photons. So then you have the spin. The spin, by the way, is an intrinsic property. It has nothing to do with physical spin. It's a bad name which I've stuck on, but the spins is nothing to do with things spinning. It's not that at all. The spin is an intrinsic property, and it's given by a vector. You can project the vector along the direction of propagation of the photon or against the direction of the propagation of the photon. So these two possible, this is called helicity, the projection in the direction of the propagation is called helicity, projection of spin. So there are two possible spin directions, two possible helicity directions. How could S.N. Bose have known this? What I'm telling you was something people came to know in the 1950s. After Dirac's relativistic equation and field theory and so on. Then people started looking at representations of the Lorentz group. So all this happened much later. How in 1923 could S.N. Bose have anticipated that there are two spin states? Now, because he does not elaborate, he doesn't write on this. He has referred to this kind of debate between his mental debate. He really didn't have a debate with Einstein, because Einstein was the Mahaguru, you see. The Mahaguru is unassailable. You don't ask the Mahaguru questions, okay? At least that was the feeling at those days. Now, coming back here, the discovery of Bose, of S.N. Bose, marked the beginning of what I would call quantum statistics. It also enabled Einstein to generalize what Bose had done to matter. To matter which obeyed the statistical counting rules which Bose had enunciated. So there is matter, there could be atoms which do that. And if they do that, then you will get a new state of matter. I'll come back to that in a minute. And it also enables you to give a universal classification of fundamental quantum particles. All that in a minute. First, Bose-Einstein condensate. Well, actually, I have drawn the picture slightly wrongly in this. So first, focus on this. This is called a laser pumping. Now, all of you are familiar with lasers, I'm sure, because you use it every day of your life. And what is done in a laser is pumping many atoms from the ground state, from their equilibrium ground state, pumped by giving energy to them to some excited state. So this is an excited energy level. And then they radiate very quickly, without much radiation, to a metastable state, okay, right here. Now then, of course, it slowly decayed back to the ground state with a huge generation of photons. So it's a gas of photons which come out. All the photons are in the same quantum state. That is why that is what accounts for their coherence. You know that the laser beam coming out of there is a coherent beam, that there's a distinct relationship between the phases of each of the little wave functions that describe the quantum state. Now, this was known in the 60s, the 50s or 60s, when Charles Townes used this mechanism to discover a laser. But then Einstein had proposed something much more brilliant. That's called the Bose-Einstein condensation. He had said that if you had atoms, so this was, imagine that this is about photons, still about photons, but Einstein went beyond, he was talking about atoms. And he said, if you have many atoms, cool them down by some mechanism, physics of cold atoms, then it is possible that many of these atoms will be in the same quantum state, a macroscopic quantum state. So each atom, you know, has the size of an angstrom. But if a crore of them get together, or maybe several hundreds and thousands of crores get together, then you create a state which is much bigger. And yet, all of them are in the same state. And this discovery, was made in 1995 by three very smart physicists. And they got the Nobel Prize, of course, for the first observation of the Bose-Einstein condensate. So what you see here is a condensate where you're able to see this is the jump in the density of states when the condensation happens. So that just means that all of them have come to the same state. This is a super atom, okay? And this opened up completely new directions. So starting with the discovery of S and Bose, Einstein's generalization to Bose-Einstein condensation, came the physics of cold atoms, which is a new probe on condensed matter physics. And that, as we know, is leading to quantum computation. So quantum computation is to use the physical laws of quantum mechanics to actually do your computation. Okay, our computers, the one, including the one I'm using here, works on is a classical computer. It works on classical physics. But if you had a quantum computer, things would be enormously faster. I mean, it's unbelievable what they would do. I wouldn't even venture to get into that. Okay. Here's a story which I must share with you because, again, I'm probably running out of time in a very bad way. I must share with you because I read about this in various places, especially in the very wonderful book by Kameshwar Wali, professor at Syracuse University, who has a collection of Satyendra Bose's works with beautiful commentaries and a little bit about his life. So in 1925, you probably know that Satyendra Bose went to Europe. He went to first France and then to Berlin. And he was given a very warm reception by Einstein and his colleagues at the Berlin University. And at that time, 1925, is also a very potent year for physics, because at this time, what was happening is that Albert Einstein and his colleagues decided to go to Munich to listen to a seminar. Now, this is at that time, it used to be a 6-7 hour train ride. Now it's only 4 hours. And they went from Berlin to Munich, which is in the south of Germany, to listen to Heisenberg. Heisenberg had just discovered his matrix quantum mechanics, and he was going to talk about it. Now, after the talk, Einstein was absolutely elated, but he was all equally baffled. He said, look, I know that something fantastic is happening, but I don't understand any of it. And he said to S. N. Bose on the way back on the train, so S. N. Bose writes that Einstein was so elated, so happy with the work of Heisenberg, that he was talking about it in such excited manner that the other passengers of the train were looking at him, thinking that this old man, has he gone mad? He was not really old at the time, was middle-aged, but they were thinking, who is this man with that mustache who's talking so loudly and so excitedly? What is he talking about? There's no war right now. So this, it's kind of weird, but we physicists tend to do that all the time, right? And on the way back, he told S. N. Bose, who was with him, here are two problems for you, Professor Bose. Can you work out how Bose statistics would behave in quantum mechanics, in the Heisenberg matrix quantum mechanics? Now, in your calculations, you've used the mechanics that was known, the old mechanics, which is classical mechanics. But suppose you change the mechanics, you change the equations which describe the hydrogen atom, give you the right levels. How would your Bose statistics appear to be? So we are then not talking about one electron like we do when we solve the hydrogen atom, but many bosons, Bose particles. Many particles which behave like photons, and Einstein was asking, how would they appear in quantum mechanics? And the second question was, do these particles, do the photons now interact because of Bose statistics in the new quantum mechanics? Now, here is where I would like to say that I have not seen any documentary evidence of any work or any progress by Professor Bose on either of these two problems. And that is a bit disappointing for me, because he was at the right place at the right time. And till today, I don't know why he didn't spend all his time trying to solve these two problems. These problems have been solved. The first problem was solved by Paul Dirac, who was fashioning quantum mechanics at the time. Some of you who have studied quantum mechanics would know about Dirac. And Dirac was the first to think of Bose and Fermi statistics as symmetric and antisymmetric combinations of quantum states. The Bose statistics is obeyed by particles, a bunch of particles whose quantum state is symmetric under interchange of any two of these particles. And Fermi statistics, on the other hand, happens when what you get this collection is antisymmetric when you interchange two particles. So this was completely worked out by Paul Adrian Maurice Dirac. Within a year that Einstein proposed the problem to S. N. Bose. Now this for me is an eye-opener, because I just think that, well, I can't compare myself with S. N. Bose, who was phenomenally intelligent, but I at least would have thought that, these two problems which Albert Einstein was suggesting are key issues. Indeed, they were, because quantum mechanics was rising. So, S. N. Bose's work was still in the old quantum theory, which was Einstein's forte, which was Niels Bohr's forte. Quantum mechanics was happening in the hands of these youngsters: Schrödinger, Heisenberg, Dirac, Pauli, Jordan, host of others in Europe, in the entire Europe. So this was a revolution that was going on. And the second problem was actually solved by Werner Heisenberg with student Hans Euler in 1936, after the Dirac discovery of his relativistic equation. This required special relativity. Now, I'm just wondering why S. N. Bose did not go to England, and I found the answer. Because Dirac was in England, in Cambridge. He was doing fantastic things on quantum mechanics at the time. But S. N. Bose purposely decided not to go to UK because he was a nationalist. He was absolutely, like so many other people, he used to hate the Brits for ruling us in a very oppressive way. And therefore, he had no desire to go to England, to UK. But UK, on the other hand, was where Dirac was. Those days, you see, they were not communicating with each other except by the occasional letter, okay, which would take quite a while to reach one country from another. So it would take quite a while. And people got to know after Dirac only after his work was being completed. It is very, very likely that S. N. Bose would have known about what Dirac was doing. So I don't know. I mean, he might have gone to Dirac and said, hey, wait, this problem is important because Albert Einstein proposed it to me. So let's work it out. But that didn't happen, unfortunately. On the other hand, there's another interpretation which Kameshwali offers, which is very interesting. You probably know that Albert Einstein did not quite like the new quantum mechanics in the long run. He was particularly unsympathetic to this interpretation of a probability, of a fundamental probability. So the point is that in quantum mechanics, you cannot talk about any quantity with certainty. You can only talk about the probability of that quantity having a certain value. Okay? And there's the uncertainty principle which Heisenberg had discovered, which told you that you have canonically conjugate pairs like position and momentum. Then this is not because your instruments are not refined enough, but an intrinsic property of quantum mechanics that you can either measure 100% accurately the position or the momentum. So when you measure the position, the momentum is totally uncertain. You don't know what it is. And vice versa if you measure the momentum, okay? Now, Einstein was never really happy about this uncertainty, the probability, and all these sort of statistical descriptions coming about. See, for him, who had worked in statistics, in statistical mechanics, the fundamental laws had to be deterministic, okay? So quantum mechanics, if it is a fundamental law, if it constitutes a fundamental behavior of nature, could not be probabilistic. Now, it stands to reason that perhaps Satyendra Bose shared some of these reservations. I don't know. But the generalization, see, is incredible. The generalization is into phonons, which are lattice vibrations. And here you have cold bosons. Cold bosons come into the same state. I've already described the Bose-Einstein condensate. Fermions, on the other hand, Pauli exclusion principle. There is with one fermion, the other cannot come there. So the minimum energy configuration must include this whole tower of fermions, which constitutes the Fermi sea. They are of increasing energy. This is still the minimum energy configuration. Excitations will be above this energy, and the minimum energy, therefore, is called the Fermi level. Okay. On the other hand, if you have bosons, like if you have crystal lattice and excitations of the crystal lattice, the distortions of the crystal lattice, these can be quantized. So waves on the crystal lattice, acoustic waves or optical waves, can be quantized, and they produce these phonons, which also obey Bose statistics. Phonon dynamics is used to calculate the specific heats of solids by Einstein and Debye. We come to particle physics. Yes?
Sorry for the interruption. As you told, 30 minutes over.
30 minutes over. Okay,
Yes,
good.
thank you so much.
So I still have 30 minutes, right?
Yes, sir. Yes, sir.
Okay. Yeah, it's about an hour, so 30 minutes is there, right? Okay, good. So I should try to hurry up a bit. Now, as it turns out, fermions and bosons, you see, the world is divided, okay? All matter particles, like the electrons, the protons are actually not fundamental. They are made up of things called quarks, okay? Electrons have elder brothers. The first brother is called the muon, and there are also tiny little particles with very little mass called the neutrinos. All these particles are fermions. They obey the Pauli exclusion principle, and they carry spin half. So this was another connection which people made when they found quantum statistics, that particles which carry half integral spin are fermions, like the electron, like the muon, like the neutrinos, like the quarks. Particles, on the other hand, which have integral spin, obey the Bose statistics. They're bosons, like the photon, so here we have a picture of mediation. Electromagnetic interaction is mediated at the most fundamental level by photon exchange. You see an electron coming from here and going away, and another one coming from here and going away, and they exchange a photon. So as a result of the photon, the momenta will change. So there'll be a scattering. Okay, so the electrons scatter from each other because of the exchange of photons. This one is a muon decay. So there's a muon which decays into an electron, an anti-electron neutrino, and a muon neutrino. And there's an exchange of what is called the weak boson, the W- boson. The difference between the W boson and the photon is that the W boson carries a mass. It has to carry a mass because, as you know, the weak interaction is very, very short range. It's the interaction that causes radioactivity. It's a very short range interaction. Otherwise, the whole world will decay, right? It doesn't. Similarly, you have also the weak interaction of the quarks. There's another W boson exchange. Oops, sorry. So there's another W boson exchange. This is, so quarks carry color, red, blue, green, and they also carry something called flavor. All these are names. They're not something that I can explain quickly. So RS is a red quark with a strange flavor. So what the W boson does is to change the flavor. It doesn't touch the color remains red, but the flavor changes. Here also you see this one is going here. It absorbs the W boson and it becomes strange from up. U is up. Now is a strong interaction between the quarks, and there you can see that the color will change. It may change, it may not change. And you can see that, of course, the flavor also changes. So there you have an exchange through another boson known as the gluon. So you have three kinds of bosons for the three fundamental interactions: the photon for the electromagnetic interaction, the W boson. There's also some neutral vector boson like the W boson called the Z boson. All of these bosons have been seen, have been observed in experiments. And then there's the gluon. Now, gluons we cannot observe. We have not observed. We have not observed because most people think that we cannot observe them. because there is a property known as confinement of the strong interactions. I don't have time to get into this, but if there's a question, I'll answer later on. Now, this is something which one has heard about, but it was proposed, it's called the Higgs mechanism, but it actually was proposed by all these people. So let me give the names, because remembering the names is itself a challenge. So it's Anderson, Brout, Engler, Guralnik, Hagen, Higgs, Kibble, and Lang. This mechanism was proposed independently by all these people, but I think Brout and Engler, they worked together. Guralnik and Hagen worked together. Higgs and Kibble were independent of each other, and Lang also was independent of them. So what is the Higgs mechanism? Well, the Higgs mechanism is a mechanism by which you get mass. Now, how do you get mass? So this is a cartoon which I enjoy very much. It shows a room full of physicists. Now you have to think of all these physicists as being Higgs bosons. So you have a Higgs field, okay? A Higgs field with many Higgs bosons. One pointing this way, the other pointing that way. They don't really point, they're just people. So that's why I'm saying they're pointing. And then some very important person comes in right here, okay? As soon as that person comes in, he first interacts with this group of people here, and they form a cluster. The poor man who's coming in can't actually move inside because they formed a cluster. And these people who are free to move inside also now have formed a cluster, okay? And this clustering happens every so often. So the moment this clustering happens, it's like the particles, if you think of this as a particle, it has picked up a mass. So that becomes clear when we look here. So here, these little yellow dots you see are photons. These photons, they actually pass through the Higgs field completely unhindered. Because remember, photons interact with only those particles which carry charge. And the Higgs field is electrically neutral. So it just passes through as if there's nothing. But an electron does interact with the Higgs field. The Higgs field, by the way, is a boson whose spin is zero. It's a spinless field. The moment the electron comes into the Higgs field is made up of Higgs bosons in the same, it's a condensate, it's a Bose-Einstein condensate of Higgs bosons, okay? And it forms little clusters. And the moment it forms cluster, the electron then looks like it acquires a mass. Because of the clustering, the electron can't move freely. It's been now interacting with all these four bosons, okay? Similarly, quarks pick up mass by interacting with the Higgs field in the same manner. You can see that here it is. They form clusters, and now they can't move freely, unlike the photons which move freely. So when they form clusters, they become heavy because the whole cluster will have to move as a massive object. So that's the generation of mass. But Higgs bosons are also exchanged, you see. They're also exchanged in weak interactions of the quark going to two quarks going to two quarks. This is a vector boson exchange, weak vector boson, W boson exchange. And there you see is a Higgs boson exchange. And similarly here, you see protons are not fundamental. They're supposed to be made up of quarks. This is proved experimentally very accurately. So protons have 3 quarks in them. You can see the 3 lines, quarks are propagating. So this is in some energy kinematical situation where this happens. They will emit the W bosons, and then the W bosons annihilate here to give you the Higgs. And the Higgs then forms 2 Z bosons, which are again vector bosons like the Ws, and then they decay into electrons and muons. So that's another Higgs boson exchange. So the Higgs particle is a boson which is exchanged in all weak interactions. Okay, so that's a fundamental property. Maybe I should ask Papia or Purba how much time I have. Do I have like 20 minutes or?
Yes, sir. You have 20 minutes more.
20 minutes. Okay,
Yeah.
Very good. So I'm going to shift now completely to gravitational waves. The gravitational waves are ripples in space-time. Now, in space-time, we know space-time is now governed by general theory of relativity, because that's how we think of gravity. And general theory of relativity means curvature. I should come to that in a little more detail. So when we talk about a gravitational wave pulse passing through us, you know, what happens is something very strange. It will, for a moment, it will change lengths, durations, okay? Lengths and durations. So distances and durations will momentarily change. It will become, the clocks will become slower. Oh, I can see a hand. Bunia has raised a hand. So is there a question at this time which I should answer?
Orikro, sir can answer a question if you have anything, or maybe it is some mistake. Sir, you can continue.
All right. So a passing gravitational wave pulse would change durations of intervals. So if you have an interval, say 1 second, then when the gravitational wave passes, it will shift it a little bit. It slow it down, increase the distance, increase the duration, and also contract the distance, okay? So these things happen when the gravitational wave passes. And how do you know that there are gravitational waves? First of all, theoretically, of course, Einstein's general relativity predicts them. In the case of weak gravity, Einstein's general relativity predicted that there must be gravitational waves, just like there are electromagnetic waves, but there are differences. First of all, how do you know that they're there? The first evidence was actually indirect evidence, which came from pulsars, okay? Pulsars are neutron stars, which are very, very compact stars, which are made up mostly of neutrons, and they have very strong magnetic fields. And they rotate. The magnetic fields form out of the rotation of these pulsars. And when they rotate, they produce actually electromagnetic waves, radio waves in case of many pulsars, okay? Now, there was this evidence of a binary pulsar. One of them is a pulsar, this one, which is emitting radio waves. And the other one is just an ordinary neutron star, which is not emitting radio waves. Now, the funny thing about a pulsar is the regularity of the emission. So if you have a single pulsar, which we know now, you know, the giant meter radio telescope near Pune, Nayangar at Pune, is a great repository of pulsar observations. So if you have time, when the pandemic goes down, you can pay a visit to GMRT and have a look at the data. However, this is somewhat different. What was found is that instead of the regularity, these pulsars, the emission actually causes the signals, the frequency of the signals to reduce. And there's a slow reduction. And for a long time, people couldn't figure out why this is happening. Why is there a slowing down? Why is there a decay as the pulsar approaches, as the pulsar approaches the neutron star? So this is the delay in the time of periastron. So it takes a longer time to reach the closest distance. Now, why does that happen? And people then figured out that maybe the surmise that maybe it's gravitational wave exchange. So maybe the pulsar is producing gravitational waves, like I show in the picture. And if it loses energy, it will take time to complete its orbit. And that's exactly what happens. And then they approached radio astronomers and pulsar astronomers. By the way, the first observation of a pulsar was made by a lady student, okay? Professor Bell at Cambridge, okay? Of course, she didn't get the Nobel Prize, but her advisor got the Nobel Prize. This is another bit of politics which we can laugh about. So gravitational waves emitted. Here, the continuous line is what Einstein's general relativity predicted, and the dots are the experimental data. Now, I'm sure that all of you who have done a little bit of experimental physics would look at this diagram and say, oh, come on, is this a joke or what? Is it possible that this is so good? But let me tell you, yes, this is a fact. This is a fact. There's no fakery here. It's complete fact that the dots fall on the theory line. That's incredible. But with this accuracy, then, you will be convinced that gravitational waves have to exist, although we haven't seen them. The question then is, how do we see them? If we want to see observe gravitational waves directly, how do we see them? Once again, we will have to use photons, you see, or electromagnetic waves. And this is how it's done. So here it is. First, forget about these angular lines, these light gray lines. Look at a light source from which light comes to the prism, which is a beam splitter. It splits a beam into two parts, one which goes into mirror A, and the other one goes to mirror B. And you can adjust, these mirrors are adjustable. You can adjust such that the distances between the mirrors and the prism, this can be changed, okay? So they get reflected there and they come back and combine. If they combine, you know that they will interfere. They will cause interference. And of course, here is the light detector. So when they come out to the light detector will show interference patterns. And of course, it will depend on the distance between the prism and mirror A and the distance between the prism and mirror B. If this distance can be adjusted such that these two light beams, light waves come in phase, then you will have a maximum at the light detector. If, on the other hand, they come to a minimum, then you'll have no signal. Okay, if they're completely out of phase by phase pi, which means that they're separated by half a wavelength. So if the distance between them is different by half a wavelength of this light, then you will see no signal. But now what happens when a gravitational wave passes through? So you set your mirrors in such a way that there's no signal and wait. And that's what people did for many, many years. They just made sure that all the noise sources were properly understood and taken care of. So when the noise is completely taken care of, what happens is the following. When a gravitational wave now comes through, you will not see it with your eyes. You will not see it directly. But what it will do is that it will change the distance, either here or there. Okay, in this case, it will change it here. I hear a sound which I can't understand. But anyway, that's a sound of something.
Yes,
yeah, okay. So it'll change the distance. And if the distance changes, it will produce a phase change. And the moment there's a phase change, you get a signal in the detector, right? Because you move away from the destructive interference. The moment you move a little bit away from the destructive interference, you will see a signal in the light detector. So this is the principle of gravitational wave, observing gravitational wave using optical interferometers. So we are using light, we are using photons, okay? And these are the two observatories in the United States which belong to this Laser Interferometer Gravitational Observatory, LIGO. One is located in the state of Washington, and the other is located in the state of Mississippi, Missouri, one of them. And they are about 3,000 kilometers apart. And what happened, the drama that happened on 14 September 2015 was that they saw a signal. Now here it is, the Hanford, which is in Washington, this saw the signal, which is given in the deep orange, in the broad orange, and the light line here is the one that was well known, it was predicted, okay? So that was predicted by making templates of all possible gravitational wave emissions. A lot of Indians were involved in this work in making these templates. So these templates were available. As soon as they saw a signal, they were able to compare with those particular templates. And these computer programs were set up which could do these things. And similarly, the Livingston, which was in Mississippi. And what they did then was to shift this, because there's 3,000 kilometers, that takes a little bit of time for the gravitational waves, which travel at the velocity of light, to go from there to there, go from Hanford to Livingston. And after adjusting that time, you find that they just fit each other incredibly well. So this is the signal, okay? This is the signal that was the drama. And suddenly we realized that gravitational waves have now been directly observed, okay? They have been observed directly. That was the first observation, 2015, 14 September. It was big drama. Of course, I'm not going to get into that, but my point is, what created these gravitational waves in the first place? So the most important, or the most common, or I should say the most popular description was that, oh, it must be that there were two black holes. And then these two black holes were rotating around each other, producing gravitational waves. And as they came closer and closer, like here, there's a drawing, there's a cartoon, or it's kind of a simulation. It's a simulation. You can see that the horizons of the two black holes are very close, and then they merge together. And they merge together into a single black hole, perhaps, because nobody knows for sure. What we know is that if you make this assumption, the LIGO data is consistent. But as they say in America, there's no smoking gun signal. There's no 100% guarantee that this is the case. So a whole group of European physicists felt that there could be an alternative explanation. Maybe there are these binary exotic compact objects, ECOs, BECO. They could be boson stars. I shall tell you in a minute what boson stars are. And these objects could merge. And when they merged, they would also produce gravitational waves because these are very massive objects. So like black holes, they come from afar, go around each other, and then they merge together. This conundrum, this problem of whether they are black holes or these exotic compact objects continued through 2019 when the Event Horizon Telescope made this observation. Now, all of you have seen this picture. First of all, I would like to tell you, those of you who aren't in this business, you should remember that this picture was not seen like this because it was in microwaves, and microwaves can't be seen. So this photograph was reconstructed and falsely colored. So the coloration is completely false. Everything is in microwave. The Event Horizon Telescope, what it observed was microwave emission. But when they looked at the spatial distribution of this microwave emission from this galaxy known as Messier 87, M87, this is the picture they were able to reconstruct. What does it tell us? Is this a black hole? Is this something else? So NASA set all its scientists to simulate what would happen if this was indeed a black hole. Messier 87 is a galaxy much larger than ours, and it has something in the middle which is emitting this enormously intense light in microwaves. Light meaning microwaves. Microwaves, by the way, is what you use for your mobile phones, as you must know. And second point about microwaves is that this was discovered in Kolkata by Acharya Jagdish Chandra Bose. The microwaves we have a great history with. So the left-hand side is what NASA put out as the best simulations, best simulation of a black hole. So if this was a black hole, then this would be the photon shadow, okay? There's a photon sphere, all the photons from behind. So let us assume that this black hole has what is called an accretion disk. It's a binary system. So there's an accretion disk, photons are coming in from the other side, and those photons which get in, they will not come to your eye anymore. So that creates a shadow. The horizon is somewhere far in between. So this is much smaller than the horizon. However, the same data could also be explained by this picture, this weird looking picture. There is no horizon here, okay? But if you look at the other parameters, there's no way to distinguish between them. This was a problem, right? Now, very quickly, I think I have, 10 minutes now? Or how am I doing, Papia? 5 minutes, 10 minutes?
Sir, actually, it's 5 minutes.
5 minutes, oh my God.
Yeah, but you can take content.
I can take 5 more, right?
Yes.
Okay, great, thank you. So here it is, this is a light cone in special relativity. A light cone, by the way, is a beautiful space-time diagram created right after Einstein's special relativity came in. It was created by Minkowski, Hermann Minkowski. And this is a diagram where you can see that light is what is supreme in special relativity here. So these edges of the cone, they give you the propagation direction of light. Future is always towards the lower side of the diagram, past is upper side. Okay, and this is the present. You can see everything is written here. Beautiful diagram. And any particle, so photons will travel along the edge of the light cone, and you and I will travel along the middle, through a line called the middle, which is called your world line. Every object in the universe has a world line. A star, a galaxy, you, me, an atom, an electron, they all have world lines which look somewhere in between. And well, this is something very funny. Along the light, you see, if you look at the space-time distance, its square is 0. There's something weird about this geometry. So usually we think of distance being 0 in space when one point is on space and time. Okay, that's easy to prove from this diagram, but I shall not take the time because I don't have much time. Okay. Now, this is what special relativistic space-time would look like. You could have one light cone explaining all the events of the universe, but that isn't the case. You have general relativity, which is in the presence of gravity. Now, there you see that the light cones get distorted and tilted. They get distorted and tilted because of curvature of space-time. This is what we mean by space-time curvature, that the light cones are definitely not like this. This is called flat space-time. This is called curved space-time. And the relative tilting and the relative distortion, as you can see, has to do with curvature. Okay, there are different parts of the curvature. And this is what happens when a star collapses. Again, I'm rushed for time. So this is the initial situation of a collapsing star. It collapses because of its own weight, because what drives a star gets completed, gets finished up. You know, the nuclear fusion process which drives a star no longer works. It's run out of fuel, and then the star begins to collapse under its own weight. When it begins to collapse, you look at the space-time around the star, you can see that there is already some kind of tilting. And if there is tilting here, far away, the light cones look like in flat space-time, so light takes a longer time to reach you. This is the observer. Here also, the light takes a very long time, but this picture is actually wrong, because if you are here and you shine a torch, the torch will never come to this observer. It will just go along this red line here, which is called the horizon. And inside, light cones bend even more. Actually, there's a picture, which is a more accurate picture due to Roger Penrose, who got the Nobel Prize last year. This is his picture. And this is a much more accurate picture because it shows you that the light cones are aligned with this surface, which is called the horizon. Light cones inside get distorted even more because the curvature keeps on increasing until it becomes infinite. It's undefined. It's called the singularity here. Okay. So this picture is what corresponds to the gravitational collapse to a black hole. So this is how we would think of a black hole. On the other hand, if you think of a compact star, like the exotic compact star that people are wondering about, then we have a situation from the outside looks quite similar. Okay, from the outside, you can't make much difference between this and this. The outside, the light cones do tilt as you come nearer to the star because the curvature increases, but there is no horizon. There's no limiting surface from which light is withheld, and there is no singularity. So the question is it this or is it this? What are we observing? And yet, today, until today, the answer is not known with 100% accuracy. So this is no uncertainty principle. The uncertainty is because we need more data, we need better statistics. But I should just say that what is the boson star? This is one of the exotic objects proposed around 2017. This is supposed to be an invisible compact star. It is not visible. We have never seen a boson star. Its mass could be 10 times to 10 crores of a solar mass, okay, very humongous. It's actually crores and crores of solar mass in the case of M87, if that is a boson star, and yet its size is very, very small. It could be like a size of a sun. So imagine mass, which is crores of times bigger than the sun, but the radius, which is as small as the sun. So these are very strong gravitating objects, okay? And you can think of them to be a Bose-Einstein condensate. That's the theory. These are Bose-Einstein condensate of very light particles. So where did this mass come from, this humongous mass? It comes from the gravitational field energy of the system, okay? That's fantastic. It's a very exotic object. Is it there in space? We'll have to wait. Maybe it's there. Maybe that's what produces those pictures that we have seen that I showed you, this one and also this one. But we don't know yet. Okay, so is the gravitational wave signal due to a black hole, or is it due to a boson star, which is a Bose-Einstein condenser? We don't know. Okay, so this is where we end. I mean, this is where basically I end. But I think some of you may be wondering, so just to anticipate a question, I haven't spoken about gravitons. I spoke about the weak interactions, the strong interactions, and the electromagnetic interaction, but I did not talk about graviton. Why not? So this is briefly to mention that quantizing general relativity has proved to be a humongous challenge. There is no complete theory yet. The idea of boson exchange was put forward in superstring theory, but superstring theory in turn only works in 10 space-time dimensions. So 1 time and 9 space dimensions. When you try to bring it down to 4 dimensions, what happens in 4 dimensions? You have a lot of junk which you can't get rid of. You don't know what's going on. Things become much more uncertain theoretically. So there's another idea which works in 4 dimensions, in which I have worked. This is loop quantum gravity. Here, what we get is a nice picture of space-time, 4-dimensional space-time, and that one, 3-dimensional space, at least I can think of it like this, that it's a network. It's a network which has links and which has not, and which has holes. And of course, these holes are very, very tiny, 10 to the minus 33 centimeters, whole dimension. Very tiny, you won't see it. Only when you go to very small energies, very large energies, very small dimensions, you can see this. And the right-hand side is how you picture a black hole. And it gives a very nice result for what's called black hole entropy, but I don't want to talk about it. So finally, was the Nobel Prize missed by Satyendra Bose? Let us look at this objectively. He wrote 2 fantastic papers which changed fundamental quantum physics forever. Okay. And one paper which is thought to have been written, but there is no evidence that it has been published or it has been sent for publication. Even S.N. Bose was not categorical about that. But the problem is the following. After going to Germany at a time when quantum mechanics was coming up, Satyendra Bose did not follow up on that work. He moved to experimental physics. Well, part of the fellowship that he got from Dhaka University was that he would work to improve the labs and so on. But it seemed that his own research interests also shifted. And I have not understood why. Okay. So they diverged from the fundamental issues of quantum mechanics. In fact, look at the papers published by Professor S.N. Bose. There's not a single paper on quantum mechanics as we know it today. About the Nobel Prize, I would like to tell especially the younger members of the audience that it is not simple. It consists of lobbying, it consists of sociology, consists of many things which you would find quite unsavory. And the case of E.C. George Sudarshan is very important because he discovered 2 major laws of nature. People who used his ideas were awarded the Nobel Prize, but he wasn't. Why is that? I would put it down to sociology. It's not physics. As a physicist, George Sudarshan was supreme, but he missed out because his sociology was not good. His politics, if you wish, was not good. So it is, if you are going to be a political type of physicist, if you can do a lot of lobbying, as we say in Bangla, nije dhak petalo, if you can petao your own dhak, if you can beat your own trumpet, or blow your own trumpet, I think that's the right word in English, that's a different matter. But if you can't, as most physicists aren't able to, I would say that it's not correct to focus on the Nobel Prize. Satyendra Bose did that fantastic work out of sheer fun, out of curiosity. What if photons are indistributed? It's fun. And it's only worth doing if it's fun. Thank you very much. I actually tried your patience. I went beyond. Thank you very much to all of you for listening.
No, sir, not at all. Actually, it was a story from photons to gravitational wave. but I understand, and it was really nice. But you know, sir, there is a limited time, so we need to stop somewhere. So there is lots of lobbying, politics, many things behind this story. But obviously, we will see, we will think positive. So now over to Dr. Purva Bhattacharya for question answer session. Thank you so much, sir.
And Purva,
Thank you.
you know, Partha sir, I think this is one of the rare occasions when we have nearly 200 participants till the end of the talk. So
Thank you. Thank you.
I think it is just second or third time it's happening in the School of Basic and Applied Science. And so please do not think that we actually all wanted to listen, all wanted to hear. But certainly, as Papia said, that sometime time is little, little more constrained than we think. So thank you, sir.
Thank you very much.
Purva, please continue. Thank you, sir.
Thank you. Thank you very much.
Thank you, Parthu sir. Thank you, Papia. And thank you, sir, for this wonderful lecture. Actually, after many years, I listened to your lecture and I missed your classes once again, actually. But since the time is really constrained, so I will just take 2 or 3 questions. And maybe we can collect all the other questions and send it to you so that you can answer and we can share it with the participant. So one question is that is time crystal somehow connected to Bose-Einstein condensate?
Sorry, come again. I did not hear.
Yes. Is time crystal somehow connected to Bose-Einstein condensate?
Time crystal?
Yes.
I don't know what a time crystal is. Can you tell me what a time crystal is?
I can't see his name actually. So whoever just questioned this. So maybe I should move to the next question here.
Yeah, I've never heard of this time crystal. I mean,
yeah, I
our
didn't
youngsters,
also.
They know much more than we do.
Yes, I never also heard these
So
things.
I've never heard of this time crystal. So I can't answer this question. I'm so sorry.
No. We have one question from Aparajita ma'am actually.
Yes.
Can we say
Hi,
that, can we say the helicity is more fundamental than spin?
Well, you see, the helicity makes sense only for massless particles, Aparajita, as you will know. For particles with mass, of course, we have to talk about spin. And so all fermions, of course, have spin. Now, as far as the exchange bosons are concerned, it's only the photon which is massless. The gluon is also supposed to be massless. So there we can talk about helicity, but the gluon we can't actually observe. So we don't know what it is. I mean, it's confined. It's supposed to be confined. Now, for the W bosons, the weak bosons, the W boson and the Z boson, of course, they have mass. So we can't talk about their helicity. We can talk about their helicity, but it becomes complicated because the helicity is not a Lorentz invariant concept for particles with mass. Okay, so helicity is certainly not more fundamental, but it's for massless particles, it's the only thing you have because you can't talk about 2s+1 states. All massless particles, even if they have spin 27, will have only 2 spin states, 2 helicity states, plus 27 and minus 27. All the intermediate states are not realized in nature, and that has to do with their masslessness. Is that okay, Aparajita?
Ma'am, you are muted. Ma'am, can you please unmute yourself?
So just I want to thank you so much, Professor Majumdar.
Thank you.
But I'm just asking that if the neutrino is massive, what nowadays we are having the experimental results, then what is the left-hand side, right-handed, left-handed neutrinos and the helicity?
Oh, but yeah, okay, good. So the right-handed, left-handed neutrino are not helicity. There's another property for fermions, for spin-half fermions, called chirality.
Okay.
So the chirality is not a projection of the spin. It's a separate property. It's a property related to parity. Okay. So the left-handed and right-handed chiralities of the neutrinos, they have to be present because it carries mass. If it did not carry mass, then for spin half fermions,
Yes.
they'll only have one chirality. But now that we know from neutrino oscillations, these neutrinos carry both chiralities, although they're different because one is much heavier. The right-handed neutrino is supposedly much heavier than the left-handed neutrino. Okay, but that's a different property. So helicity concept becomes important only if you have massless particles, like the photon.
Thank you.
Okay. Yeah.
There are another question from just a minute, sir. From Partho Nundi,
Yes.
who is asking, I have a question about the relationship between the zeroth component of spin and the rest frame.
Yeah. Yeah. So that's the point. It's related to the previous question. The zeroth component of the spin, zeroth meaning the azimuthal quantum number being 0, right? That's what you mean by the zeroth component. That is only realized if you can define a rest frame for the particle. Now, for the photon, we cannot define a rest frame because the photon is moving at the velocity of light. Okay. And therefore, we have to only, it's not just a zeroth component, by the way. Like I said, if you have spin 27, then of course the azimuthal component goes from 27, 26, 25, all the way down to minus 27, right? But nature, because they are massless, will not ever show you the other components. You will only begin to see the plus 27 and the minus 27, because these are the projections of that huge spin on the direction of the motion and against the direction of motion. Okay, so these are the two possible helicity states. So it's not just a zeroth component, it's a lot of components. When you do this thing, when you do this quantization of angular momentum, you have all these other components of the spin, which will not be realized unless you can define a rest frame. Okay, and for massless particles, you cannot define a rest frame. All right, Partho?
I think it is very clear. So just the last question from Shagnik Roy.
Yeah.
Can the gravitational waves have angular momentum like the electromagnetic waves? And if not, then why it is not possible?
Of course it is possible. Of course it is possible. And I think Shagnik, maybe from presidency, I don't know. If it is,
I
then
think so,
Shagnik,
actually.
your two dadas and your professor Ratna Kule and myself have actually written the first paper on the angular momentum of gravitational waves. It's published. And there we have tried to say that if you have angular momentum, which you do, because when you have two black holes, let us say, which are going around each other and then they come together and merge, then of course there's a huge amount of orbital angular momentum. So when they merge, gravitational waves are given out, and all we are measuring at LIGO is the energy. We don't measure the gravitational angular momentum. So what we proposed is that, what we showed, in fact, was that if you have angular momentum for gravitational waves, then your plane wave description, which is what most people use, will no longer be valid. You'll have to use what are called gravitational wave beams. Now, optical wave beams are known in atomic physics. Those of you who do atomic physics would have heard about optical beams. And these beams have a finite width. They also have lots of other properties because they carry angular momentum. So what we are proposing is that a gravitational wave will be more like a gravitational wave beam and not a gravitational wave ray. Okay, so that's one of the things that was there in that paper. But it's a paper which came out of presidency, I think about 2 years ago. And the other two authors, the student authors, are both in the US. They're now in India on vacation, but they're both studying in US universities. And Professor Ratna Kule is teaching at presidency. So there you are. That's the answer to your question, Shagnik.
Thank you so much, sir. There are lots of questions. Yes, sir.
I'm Bhavani from Benares Hindu University. Parthoda, how are you?
Good. Nice to hear from you.
Yeah,
again.
so I listened your complete talk. Still, I'm listening.
Thank you.
Yes, very nice talk. Only one thing I want to ask that can you explain that how Higgs himself get mass in the framework of your cartoon? That
Oh,
cartoon.
okay.
Yeah.
Okay, so then I should go back. Okay, I'll just say it in words because I don't want to go back. It's running out of time. Basically, the idea is that you have the Higgs field. The Higgs field is like a condensate, like a Bose-Einstein condensate. And let us say that a photon comes into the condensate. It doesn't actually see the condensate because the condensate does not have any electric charge. So the photon just goes through it. But if an electron comes, then it has an interaction with the condensate known as the Yukawa interaction. So as soon as it comes, then there's a little clustering of the Bose-Einstein condensate, the Higgs boson condensate, which forms around the electron, and that clustering gives the electron the mass. It becomes heavier now.
Yeah, I'm asking about Higgs himself get mass from that cartoon.
No, that idea is different. So
Okay.
the idea is that
so from that cartoon, can it be explained? I like this cartoon.
Yeah. The cartoon is very interesting. So the point is that you have the Higgs field, and then some important person comes in. See, if it's an unimportant person, that person can just pass through like the photon. But if it's an important person, the important person comes in, and then immediately some of these scientists will cluster around because they might want to know whether they have got the Nobel Prize. So say, hey, oh, sir, have I got the Nobel Prize? Have I got the Nobel Prize? So that's the kind of clustering. And this poor important man who came in can no longer propagate freely because there's a clustering around him. He has to walk with the cluster.
But
So
that
then,
will give mass to that important person.
Yes, it gives mass to the important person, right?
But not to the Higgs. How the Higgs getting mass? Yeah.
Okay. So the important person could also be a Higgs because the Higgs boson also interacts with itself, you see. That's a good question. It's a very good question. So the Higgs boson, unlike the photon, interacts with itself.
It is coming from the interaction, yeah.
Yes, it is coming from the interaction of a single Higgs boson from all the other Higgs bosons in the condensate.
Okay, thank you, Partha.
Thank you.
Thank you, sir. Thank you so much for the nice discussion. Actually, we have learned so many things from this discussion.
Thank you very much, Purba. I appreciate all the nice
I would like to now request Professor Aparajita Bhattacharya for the vote of thanks and to end this webinar. Though we really want to continue this discussion, but we have to end somewhere. So yes. I will like request Professor Ma'am, can you please give the vote of thanks?
Yes, thank you very much. Yeah.
Thank you, sir. Thank you.
Thank you, Purba. First of all, I just want to get apology for my late joining due to some technical reasons. So we are now at the end of our today's event. So behind this event, there are lots of people who are working on this. So this is the time to give thanks all of them. First of all, I want to thank Professor Partha Mojumdar for the nice enlightening talk, and it is a wonderful talk, a journey from Maxwell's equation to the gravitational field.
Thank you very much.
Thank you so much, sir, for giving us time in spite of your busy schedule. And at the same time, we feel honored that we have started this Satyendra Bose Memorable Lecture this year. And you are the first speaker of this lecture. We really feel good about it. Thank you so much. Next, I want to thank our Professor J.K. Pandit, the Dean, School of Basic and Applied Sciences, for all his encouragement, support, inspiration for this kind of event. And he always inspired us for making this kind of events to keep our academic life active during this pandemic situation. Thank you so much, sir, for your support. Next, I want to thank our HOD, Dr. Moumita Dev, for his enthusiasm and in support in all our this kind of events, starting from conference to the webinar, lectures, everything. So thank you, Dr. Dev, for your support. Next, I want to thank Papia, a very young faculty of our department. Yes, Papia Dhara. So for very nicely coordinating this whole program, whole event, writing the mails to everyone and sending the mails and every bit of it. Everything.
Thank you so much.
Thank you so much, Papia. I would like to my sincere thanks to Dr. Purva Bhattacharya, another faculty of our department, for moderating this whole program so nicely. Thank you, Purva.
Thank you, ma'am.
Yes, I want to give thanks to Shatarupa, Dr. Shatarupa Vishwas, a faculty of our department, for technical support on this webinar. It is quite a big thing. Thanks, Shatarupa. You have done it very well.
Thank you, ma'am.
Yes, and finally, my sincere thanks to all the students, faculties, and the participants who have joined this webinar and the lecture. Without your active participation and response, this event can never be successful, and I am very much grateful to you for joining us, and I hope in future also we'll get all your support like this. And last not the least, I want to give thanks to Ranabrata Chandra, Mr. Ranabrata Chandra of our IT department for supporting, providing us the Zoom link, everything. And Mr. Chandrashil Tiwari of the advertising department of Adams University for creating a very nice flyer for this event. And I think everyone of it loved this flyer. Thank you so much, Mr. Tiwari. And finally, I again want to thank you everyone for making this event so success. And I really hope in future we'll have sometimes in-person meet in the beautiful campus of Adams University, and we'll have such type of exciting event on physics where you can discuss and it will be academic activity. So thank you so much. Thank you all.
Thank you, ma'am.
And also, I think we should thank Dr. Bimal Sarkar, sir. I can see him smiling here.
Very well here. Yes.
Yes.
One announcement that feedback link certificate generation leave is in chat box. So it will be available for some time. So please copy and paste or just fill up it.
I thank Aparajita and Papia Dhara for inviting me to come here and enjoying such a wonderful lecture.
She is Professor Papia Nondi from Jadavpur University. Is a very senior professor. So Papia, thank you so much for joining us.
Thank you for inviting me. Thank you.
Thank you, Papia.
Yes.
Papiadi, Namaskar Papiadi.
Yeah.
I have become universal Papiadi.
Yeah, Professor Mojumdar, are you there in the meeting? Yeah.
Yes, I'm still there.
Oh.
And I would like to do Namaskar to Papiadi, who
Yeah,
have
Papiadi.
been for many years.
Vishon enjoy korechi. Thank you very much.
Thank you, Papiadi.
ভালো লেগেছে।
Okay, thank you.
I want to see in our campus, Adams campus sometimes. It is very nice campus. You love it. Professor Mojumdar, I'm telling you.
Oh, yes, certainly.
Yes, sir.
Aparajita, I will come. I will certainly come.
Yes, then we can have some exciting discussion on physics with a real cup of coffee,
Absolutely. I will come. I will definitely come. Yeah, thank you.
I thought with lunch and coffee both.
Okay, great.
Thank you so much.
Great. Thank you. Thank you very
Just
much.
for cup of coffee is not worth it.
Papiadi, you also come once.
I had been there. I have enjoyed very much your campus.
Okay.
Okay. Thanks to everybody.
Thank you so much.
Thank you.
Please come. Thank you.
Thank you all. Thank you all. Thank you, sir.
Thank you,
Thank you, ma'am.
Thank you, sir. Thank you, everyone.
Thank you.
Thank you so much.
ভালো থাকবেন আপনারা সবাই।
Yeah.
শরীরের
ma'am,
যত্ন
আপনিও।
নেবেন।
Yeah. Thank you so much. Shatarupa Vishwas is host now, so this link will be available for some time. Meanwhile, you can fill it. You can fill it for the certificate. Okay, so I'm leaving, everyone.
So I am leaving also.
Yes.
So you can leave now.
Yeah.
Everyone?
Bye.
Okay.
Yes.
Thank you. Thank you.
Okay.
for all
Please
your
stay for
support.
some time.
It is really exciting event.
Yes.
All together.
Shatarupa, please stay for some time.
Yes, I'm here.
Okay.
Thank you so much.
Thank you.
Bye-bye.